Let's talk about Avogadro's law and how to solve some problems. Joseph Louis Gay-Lussac of France studied the volume relationship of reacting gases at constant temperature and pressure and published his results in 1809. He gave us Gay-Lussac's law of combining volumes of gases. When measured at the same temperature and pressure, the ratios of the volumes of reacting gases are small whole numbers. You can find an excellent presentation called Gases and How They Combine, also on YouTube, from the chems people. Avogadro's law and its meaning. For instance, hydrogen chloride forms from the reaction of hydrogen and chlorine gas at constant temperature and pressure. And we see that 1 mole of hydrogen reacts with 1 mole of chlorine to form 2 moles of hydrogen chloride gas. That's a later interpretation. 1 volume of hydrogen combines with 1 volume of chlorine to form 2 volumes of hydrogen chloride. That is the kind of thing that we can show with Gay-Lussac. That means 1 liter of hydrogen reacts with 1 liter of chlorine to form, at the same temperature and pressure, 2 liters of hydrogen chloride. And we infer that therefore 1 molecule of hydrogen is reacting with 1 molecule of chlorine. And since the word mole simply means a collection of molecules, 1 mole of hydrogen reacts with 1 mole of chlorine. Again, that happens whether it's at the same temperature and pressure or not. But we inferred that using the law of combining volumes. Avogadro's law states that equal volumes of different gases at the same temperature and pressure contain equal numbers of molecules. And so if the amount of gas in a container is increased, the volume is increased. And if the amount of gas in a container is decreased, the volume decreases. So, using this balloon example, as we increase the amount of gas, for instance by blowing air into the balloon, the volume of the balloon will increase proportionately. Now, we know Avogadro's work was critical for the development of chemistry. In fact, we celebrate 1811 as the birthday of chemistry when Avogadro was published. It offered a rational explanation of Gay-Lussac's law, and it helps us to understand the diatomic nature of gases in elemental form, such as hydrogen, chlorine, and oxygen, and nitrogen. That means, of course, that those gases come in packages of 2, hydrogen, oxygen, chlorine, nitrogen, and so forth. Avogadro's law also provides a method for determining the molecular masses of gases. It affords a firm foundation for the development of kinetic molecular theory. So let's look at problems. The mathematical form of Avogadro's law is the volume divided by the number of moles is a constant, which we can turn into V1 over N1 equals V2 over N2. N is our universal symbol for the number of moles. So, this sample problem, if you have a gas with a volume of 9.20 liters containing 1.225 moles of the gas, and we increase the amount of gas to 2.85 moles without changing the pressure and temperature, what's the new volume? Well, given that, we solve for V2. Always solve the algebra first. If we multiply both sides by N2, we get V2 equals N2 times V1 over N1. So we plug the numbers, N2, 2.85 moles, V1, 9.20 liters, and N1, 1.225 moles, into the equation, and do the math, we come up with 21.4 liters. And that's sensible because we've increased the number of moles of gas. Another exercise for you to do. If 0.25 moles of argon gas occupies 7.62 milliliters, at the same temperature and pressure, what volume would 0.43 moles of argon have? And frankly, you could change the gas, couldn't you? Because equal volumes of different gases contain equal numbers of molecules. Here's the solution. We do it exactly the same way, and we find 13.1 milliliters to be the answer. You may want to pause the video to study this further. Here's another exercise. A balloon with 10 grams of oxygen has a volume of 7.00 liters. If you add 5.00 grams of oxygen and don't change the temperature and pressure, what's the new volume? Now, the mass is proportional to the number of moles since we're using the same gas. So we use the same equation, solving for a volume of 15 grams. So we multiply the 15 grams because we added 5 to 10. We multiply that times the original ratio, volume over number of grams, and we get 10.5 liters. Again, you may want to turn off the video to study the solution. Avogadro's law on the mole. We can also relate 1.0 mole of gas to a certain volume. We do experiments and find that 1 mole of any gas at 0 degrees Celsius and 1 atmosphere or 101 kPa pressure is contained in the same volume, no matter how many times we do the experiment or what gas we use. And that volume is 22.4 liters. That's a number you should probably remember. We use this to solve problems. For instance, what would be the volume of 3 moles of hydrogen gas at standard temperature and pressure? We call that STP, 0 degrees and 101 kPa pressure, 1 atmosphere. Well, we know that 1 mole of any gas is contained at 22.4 liters at STP, and so the volume of 3 moles of the hydrogen would be 3 moles times that ratio, 22.4 liters per 1 mole of gas. The answer then, 67.2 liters. Here's another problem. How many moles of methane gas would be contained in 3.36 liters at standard temperature and pressure? Well, we go back to the same statement. 1 mole is contained in 22.4 liters of any gas at STP. We solve for the number of moles. Moles of 3.36 liters of gas is equal to 3.36 liters times, now we've turned the conversion ratio upside down to get moles because that's what we want to solve for. So 1 mole is 22.4 liters and 0.15 moles is the answer. Another problem, what would be the number of grams of oxygen contained in 44.8 liters at standard temperature and pressure if the molar mass of oxygen is 32 grams? This is one more step. Again, 1 mole is contained in 22.4 liters of gas at STP. So the grams of oxygen in 44.8 liters is equal to that 44.8 liters. Now we have to, as we've said elsewhere, go into the mole hole. We multiply by the ratio. 1 mole, 22.4 liters. That works because we're at STP. Then we multiply by the molar mass of the oxygen, which is 32 grams. Liters over liters is 1. Moles over moles is 1. We're left with grams. When we do the math, we get 64.0 grams. Those are the types of problems that you can see with the Avogadro's law.